Any questions?
Hocam şimdi bu rotation matrix Z için mi? Around Z.
Yes. So the Z coordinate doesn't change. There is a 1 in the Z coordinate. Time doesn't change. There is a 1 in the time coordinate and zeros everywhere else. And this 2 by 2 matrix is nothing but the rotation matrix in the XY plane.
Aslında sistem time etrafında da mı dönüyor?
There is no rotation around the time. Time doesn't change. You see, rotations, although we are used to thinking of rotations as rotations around an axis, rotations are actually rotations in a plane. So you rotate in the XY plane, or you rotate in the XZ plane, etc. So rotations are always defined as two-dimensional in that sense. In three-dimensional space, of course, if you are specifying a plane, you are also specifying a perpendicular direction, a single perpendicular direction. So in that sense, we are used to thinking that we are rotating around the z-axis when we are actually rotating in the xy plane, or we are rotating around the x-axis when we are rotating around the yz plane. So because whenever you specify a plane, you specify a unique perpendicular vector to that. A perpendicular unique direction, let's say. Not a vector, but perpendicular direction. But that correspondence breaks down when you go to 4 dimensions. So, as you said, your friend was tempted to say that, okay, here the z coordinate and the time coordinate does not change, so we are rotating around the z-axis and the time axis. But it doesn't really make too much sense because we are actually rotating in the xy plane. Now let's see. We had already defined this interval. Now I can talk about the interval vector, which I will call, this vector is, we have one event xa and the other event xb. This is what we call a 4 vector. It's a 4 vector. It's not a 3-dimensional vector. It doesn't just only specify the direction. It also specifies some kind. It has a time component also. It's a generalization of our concept of 3-dimensional vectors with some slight modifications. Now the interval is just delta x mu squared, which we define as minus delta x0 squared plus delta x1 squared plus delta x2 squared plus delta x3 squared. What do you mean by behave like a normal vector? Almost. And that almost, the reason why I'm not saying yes, but almost will be this minus sign. You see, the square of any vector is always positive in 3-dimensional space. But you see, you have 2 events. In a given reference frame, let's say those 2 events can happen at the same time, at the same position. So these will be 0. Then the interval squared will be, they happen at different time, will be a negative number. So delta t squared can be negative. Delta tau squared less than 0. For such events, we call them 2 events. The separation of 2 events is time-like. if delta tau squared is less than 0. And in fact, if two events are separated by a time-like distance, it is always possible to find a reference frame in which they happen at the same position.
Farklı zamanda gerçekleşiyor ama aynı.
You see, when you are talking about they happen at the same time, they happen at different times, one happens before, one happens after, they are at the same position, they are at different positions, etc. You have to be careful about your reference frame with respect to which reference frame are we talking about. For example, it might happen that there is an event that you hear this sound is created at this point. At a later time, this sound is created at that point. In the reference frame fixed at u, in which you are all at rest, these two events happen at different points, at different times. In my reference frame, they always happen at this point. They happened at the same position in my reference frame. In your reference frame, in the reference frame fixed on you, they happened at different position. In the reference frame fixed on me, they all happened at the same position at different times. So you see, to find a reference frame in which these two events happen at the same position, it is enough to just go to a reference frame which is moving at, let's say, a constant speed which is equal to the distance in your reference frame between those 2 points divided by the time in your reference frame between those 2 points. Then in that new reference frame, that event happens at the same position. Those two events are what we call time-like events. They are separated by a time-like interval. Now, it might happen that delta tau squared is 0. In this case, the separation of two events is light-like. So you see, to find this reference frame in which those two events happen at the same point, you just go to another reference frame which is moving at such and such a speed. As delta tau squared gets larger and larger, close to 0, that speed increases. And when delta tau squared is exactly 0, the speed of the other reference frame equals the speed of light. So that's why it's called light-like. These two events are separated by a light-like interval. And then there is the third classification. I mean, you can never reach those two events. No object with mass. Delta tau squared is larger than 0. For example, it might happen that in my reference frame, two events happen at the same time, but at different points. So in my reference frame, delta x0 is 0, whereas these are non-zero. So those are the cases when delta tau squared is larger than 0. But if in my reference frame, those two events happen let's come to that point later on. So in that sense, at least in one reference frame, those events happen at the same time at some space separation. Then we say that the separation of two events is space-like. So this is when it is time-like, it is always possible to find a reference frame in which those two events are separated by a, this is a vector in the time direction if you want, and they happen at the same position. And if delta tau squared is larger than 0, then it's always possible to find a reference frame in which delta x mu is equal to 0 delta r. So it's always possible to find this frame in which the two events happen at the same time, but they are separated by a distance, by a space-like distance. So this is why the name is that this interval between these two events is space-like. Both of them, we are always talking about two different events. But in this case, it's always possible to find a reference frame in which those two events happen at the same point. In this case, it is always possible to find a reference frame in which those two events happen at the same time. They are simultaneous. But of course, for different reference frames, the simultaneity will be broken. Delta tau squared larger than 0. No. You see, we are not going to our reference frame if we allow speed larger than the speed of light, you can always find a reference frame in which either the space or the time coordinates are 0. But we are not allowing that. The velocity is always less than the speed of light. For example, if two events are separated by a space-like separation, it is never possible to find a reference frame in which those events happen at the same point. Okay. Yeah, for example, look at this event. The first event, the second event. In your reference frame, they happened at different points, right? But in my reference frame, they always happened over there. So they happen at different points. In your reference frame, those two events happened at different times and at different points. But nevertheless, the separation was time-like. So this tells me that there is always possible to find a reference frame in which they happen at the same point. That is my reference frame. In my reference frame, they all happened at the same point, at different times. But that also brings us some new concept. That, for example, these two events, they can influence each other. Do you agree? You see, these two events, they don't happen at the same time. They can influence each other. So we can talk about different events. For example, let's see, there is a detector over there, and which will be active for some time, which will be active, let's say, at a given time, and here I send some light. So that detector, my light can influence that detector. Okay? But let's take now specify these two events. One is I send light. The other one is I just activate the detector and activate the detector for a very short amount of time. Okay? So if the time interval is set properly, my sending light will be able to influence the detector. Because activation of the light detector, let's say at a different time, okay, so let's just take this case. They are separated by a time-like distance. Let's say not light, but I send some particle. And there I have my detector that is active only for a short amount of time. So here I can create an event if I know when it will be activated, I can send my particle such that it will reach my detector at the time when the detector was activated. If my activation time, that is a different event, and my sending this particle, that's another event, if they are separated by a time-like separation, I can always find its velocity such that it will reach there just on time. But if these two events, me sending the particle and the detector being activated, they happen in my reference frame at the same time, then there's no way that my particle will be able to influence the outcome of the detector, because when my particle reaches there, the detector is not active anymore.
When delta tau square is negative, so tau is a complex number.
No. You see, delta tau squared is not the square of a number. It is the square of a vector. And the square of a vector need not, I mean, who tells you that it has to be positive? In Euclidean space, yes, the square of any vector should be positive. But in this space that we call Minkowski space, if you take any vector squared, need not be positive. So why do we call these intervals? If delta tau squared is greater than 0, let's say, then there's always a reference frame in which the separation between these two events is equal to delta tau, which is the square root of delta tau squared. So that's why we call it an interval. It corresponds to, at least in this case, it does correspond to a given length between two events, between the positions of two events. Well, now we just, so this separation, you see here we have time-like events, time-like separations, space-like separations, light-like separations. So we usually show it on a diagram. You see I will just assume that my first event happened at the origin at t equal to 0. So that delta tau squared is just, I will just assume y and z to be a constant just for simplicity, or just ignore it. I will be ignoring them for the time being. So delta tau squared is just x0 squared minus x1 squared. So delta tau squared equal to 0 means x0 is equal to plus or minus x1. It is this one. Now, of course, if you would allow the y and the y coordinate, this just doesn't become just two lines, they just become some cones. So there's one cone, x1 and x2 coordinate, the other cone, y1 and y2 coordinate. And if you allow the z, then in that case you cannot draw it, but it's called a hypercone in hyperspace, the four-dimensional space. Now this region over here and this region over here is what we call the region delta tau squared is less than 0. And this is the region that for which delta tau squared is larger than 0. Okay, so in a sense we are this cone, so-called the light cone, it corresponds to delta tau squared is equal to 0 divides my space into 3 parts. One is outside this cone. If you just imagine I have this, it's not a two-dimensional, but let's say the three-dimensional figure, let's add the y coordinate. So these are actual cones, and this region, they are connected. So they just form a single region. This region and this region, they just connect through this point, but we usually classify them as different. And so they say that the upper cone is called the future cone, and the lower cone is called the past cone. We are at the origin.
Hocam bir continuity equation gibi bir şey yazabilir miyiz?
For what? Now you see, if you are following any object as a function of time, its position will be changing. Well, we are kind of always used to drawing the x coordinate as the vertical coordinate and the time as the horizontal coordinate. This diagram is kind of 90 degrees rotated, xt diagram. So if you are just following an object that passes through your point, let's say, so it will be moving through such a trajectory. It might be moving such a trajectory, but we know that it's the slope of this trajectory is not the velocity, but the 1 over the speed of the object, because it's rotated. And we know that the speed has to be less than 1, less than the speed of light. So the slope always has to be less than 1. So the trajectory has to be, at this point, you can draw a light cone at that point. The velocity vector should be pointing within that light cone. So that's a constraint on the particles we have. So you see, if you just imagine something happening over here, if you want that object to reach you, at some point it has to move, its slope has to be smaller than 1. So but it's not allowed, its slope has to be always less than 1. Larger than 1, sorry. So it has to always go up and remain within this cone at every point. But that means something happening over here is not possible for for an information about that signal reaching you at this time. So that basically means that something happening at this point cannot influence you at this time, at this position. Of course, it might be able to influence you at a later time at a later time you might be somewhere over here, let's say, and then it might influence you, but not at this time. But something that happens over here can influence you at this point. You see, for something to influence you, some information about it should reach you. Either it can be in the form of light, let's say, or in the form of some other object just hitting you, for example. I can just throw my pen towards you, and it will influence you in the future, in my future, let's say. But the action of me throwing this thing is in your past. Now, we are talking about this simultaneously. This will be important, for example, in that case. We will say that we cannot really say that two events are simultaneous or not, because they might be simultaneous for an observer, but not simultaneous for the other observer. An event might occur before a second event for one observer, but they might occur in different order for another observer. But this is not true for every event. So if something is in your past cone, for every observer, it will be in your past cone. Because these things can cause an effect on you. Otherwise, if it, for a different observer, this just becomes in your future cone, cause and effect, they just lose their meaning. And still, special theory of relativity conserves causality. It conserves causality basically because under Lorentz transformations, which basically just transforms one observation of one observer to the other one, under Lorentz transformations, the past cone doesn't change. Whatever was in your past cone for one observer, that object will still be in your past cone for a different observer. Because you see, the definition of your past cone is nothing but delta tau squared is less than 0, plus there is one more condition, delta tau 0, let's say, is less than 0. The time coordinate should be smaller. That is your past cone, and Lorentz transformations do not change this, they do not change this. So these two conditions are invariant under Lorentz transformations. And your future cone is delta tau squared is less than 0, but the 0 component is larger than 0. And again, Lorentz transformations conserve both of those properties. So if an event is in your future cone for one observer, for you, if it's in your future cone, it's in your future cone for every observer. But you cannot say the same thing for events that happen in time-like separations. In space-like separations, sorry. So these two events, let's say this event and this event that happen at this time for you, they will have different orders for different observers. Or even take this event that happens in your reference frame at this time, and the other event happens at this point at a different time in your reference frame. They can happen at different times in different order in a different reference frame. So ordering of events do not make sense if the separation of those two events is space-like, but nevertheless it has a meaning if those two events are separated by a time-like separation. That's the main lesson, let's say.
Hocam buna göre future konuda olan bir değişiklik de gene bizi etkileyebilir.
No. You see, causality means that the events in your past cone will influence you. That is what causality is, and that is conserved. So you see, if there is an event over there, if there's something happens in your future cone, how will it go back? You see, its speed has to be, it has to be moving towards its future cone, not in your past cone. But you see, keep in mind, you see, something that happens in your future, can it influence you? Sure, it can, but it will influence you in your future. Something that happens in my future cannot influence me now. Of course, it can influence me later on. Something that is out of my, some event that happens out of my light cone, it might influence me when I reach over there. But when I reach over there, my past cone is also moving with me. It's not fixed over there, it will be moving. So when I reach this point, let's say, assume I'm not moving, I'm at rest in my reference frame. So somebody just lights a flash bulb at this point, at this time, towards the positive x direction. So that light will move in this direction, along this light cone. This is the trajectory of that light ray at a later time. Now, I will feel that light when I reach this point. I'm not moving. So when I reach that point, this is my new light cone at that position. But now that light, that event is in my past light cone. So that event can influence me in my future, but it cannot influence me now.
Peki bu CT yönünde hareket etmek zorunda mıyız?
So where will you be at later time?
Şuradaki başka bir alanda olsa da.
So you see, you see, what I said over here is I'm at rest in my reference frame. So if this is my reference frame, I'm not moving in the x direction. My x coordinate will always be 0 at all times. So basically that means in my reference frame, I'm always on that time axis. For a different observer, of course, I might be in a different position. I will be in a different position. But that is for a different observer. In this example, let's say, I was saying that in my reference frame.
Hocam şeye göre bizim rest olmamız için zamanın dolması gerekiyor.
What do you mean by rest? Rest means your position does not change. That is what I call rest in your rest frame. So at all times, I'm at the same position, which I chose to be the 0 position. Sure. But you see, make your definitions. There is nothing called to be at rest at position and time. That basically means that you don't, if you were at rest both in time and in position, that means that the next time you won't be there. Because I'm moving in my next time in the future. I'm moving towards the future. You stayed on the past, so you won't exist anymore. But that doesn't exist. You are always moving. You are here all the time. Your atoms will be here for eternity, at least until the universe lasts, let's say. So when I look at you, whatever the time is, I can measure your position. And if that position is changing, that means you are moving. If that position is not changing, that means you are at rest. That is how I define being at rest. But if at all times when I look at you, I see your position, that means you are following a trajectory on this diagram. You see, before we used to draw these diagrams. An object that is at rest was this one. Just flip this by 90 degrees. That is the diagram I have over there. This is the diagram. Flip the other diagram rotated by 90 degrees. It's the same thing. So being at rest or being in motion, when we are talking about being at rest or being in motion, what we define as motion or being at rest is your change in space coordinate. That is the definition we are using.
Hocam, bu eventten etkilenmemek için benim zamanda geriye gitmem mi gerekiyor? Bu olayın beni etkilememesi için.
You see, that event, every event in the universe eventually might influence you. There is nothing as not being influenced. It might influence you. If you want to escape from that light, the only way that you can do it is if you manage to move along your light cone. But that is not something you can do. Because you see, you are moving along this trajectory. And your light cone will also be moving along with you. At this point, this is your light cone. Now, if you want this point to stay out of your past light cone all the time, you have to move along this line. Of course, if you want to avoid that event, the easiest would be just move in the y direction. The light ray is moving in the x direction. No, not delta tau less than 0. We are talking about delta tau squared being less than 0.
Bunu gördüğüm anda aklıma şey geldi. Kompleksler de geldi. Bunlarla alakası var mı?
Okay, so let me just, it's possible to define x4 as IC tau, ICT. Then lambda just becomes a rotation matrix. Now that will be your homework, let's say. I will add it in your homework. You can use complex numbers. I mean, complex numbers saves you from that minus sign. You see, delta tau squared was c delta t squared with a minus sign plus delta x squared plus delta y squared plus delta z squared. I can also write this as I c tau squared. Well, there's no minus sign. But you see, I mean, what do you really mean by, is it related with complex numbers? Complex numbers is just a tool that you can use if it serves your purpose. I can write everything in terms of complex numbers if you like. I can also define, I don't know, z to be delta x plus I delta y. So then delta tau squared will be just I c delta t squared plus z star plus, or let me call this u star plus delta z squared. So complex numbers is something that you can always use. So what do you mean by related? Other questions?
Doğrudan alakalı mı bilmiyorum ama Cherenkov radiation diye bir şey okumuştum. Partiküller bazı ortamlarda medium olması gerekiyor olursa ışıktan daha hızlı hareket edebiliyorlar. Işık daha hızlı ortamda. Bu diyagramda partikülleri nereye koyuyoruz? Yani bu line'lar, felsefe uçur konusunda belirleyen şeyler,
You see, this is your trajectory. Well, this doesn't really have anything to do with Cherenkov radiation. This is just, you can just draw these diagrams for any particle. I mean, when we were discussing kinematics in first year, we were drawing these world lines, but x was the horizontal axis, t was the vertical axis. So these are exactly the same diagrams. But now, since the speed has to be limited to speeds has to be smaller than the speed of light, basically the slope, there are restrictions on the slope of the trajectory. You see, the slope of the trajectory is the inverse speed. So that has to be always larger than the inverse speed of light. And so basically, in classical mechanics, starting from any point, you can reach any other point at a given amount of time. But in relativity, in Newtonian mechanics, you could just start from any point. With suitable initial conditions, you could reach any other point. But with special relativity, now if you start from here, you can end up at any point in your future light cone. And if something ended up at your position at this time, it should start at some point in your past light cone. Something that started out of your past light cone cannot reach you at this time. But of course, as you are moving along your trajectory, both your past light cone and also future light cone, they are also moving with you at every point. So an event that is not in your past light cone now, it doesn't mean that it won't be in your past light cone in the future, because your past light cone will change in the future. And eventually that point might become in your past light cone. And for example, when you, if you read these, let's say, works on general relativity more or less says the same thing. Your speed has to be slower than the speed of light. But it says that, so basically you have to be moving in your future light cone all the time, but your light cone might change from point its orientation might change from point to point. Basically because the space-time is curved, so that influences your light cone. So locally, you have to move slower than the speed of light, but nevertheless, that doesn't prevent you to start from here and end in Andromeda Galaxy, let's say, in 1 second. That doesn't mean you have moved faster than the speed of light. It only means that you passed through a wormhole. And locally, you were always moving slower than the speed of light.
Peki hocam, bir şey geçmişe değişirse beni hemen anında mı etkileyecek?
Of course not. I mean, how do you change the past? That is the first question. You see, when you want to speak about time travel, as in the case of Back to the Future, for example, I mean, you do end up having problems. How do you interpret those things? What do you mean, what happens when you go back in time? Can you change your present by going back in time? So we still don't know the answer.
Hocam, mesela başka bir observer'a göre geçmiş bizim şu anki zamanımız ya da şu anki zamanımız başka bir observer'a göre future olabilir mi?
Well, you see, whatever is over here is your past. What you mean by your past is whatever is over here. And for every observer, those events are in your past. What happens over here? It might be in your past for one observer, but in your future for some other observer. So when you are talking about the past, this is what you are talking about. Let's say, this is what we are looking at t equal to 0. We are looking at the events in your reference frame at t equal to 0. All these events, for every observer, they appeared at t less than 0. They can never become t larger than 0. But this event, in that reference frame, happened at t less than 0. For another observer, that event, exactly the same event, happened at t larger than 0. So for this event, it doesn't make sense whether it has t less than 0 or t larger than 0. You always have to specify according to which observer, because it will change. For these events over here, it won't change. But for this one, it will change.
Ama hani konunun dışına çıkamadığımıza göre oradaki event bizi nasıl etkileyebilir?
It cannot influence you at t equal to 0. It can influence you at, I don't know, t is equal to 1 hour. You see, this event that happened over here can influence all the events in its future light cone. This is its future light cone. So that event can influence everything at these points. Well, you are not in its future light cone at t equal to 0, but if you move accordingly, you can enter that light cone. If you enter it, now it becomes your past, and hence it can influence you. You see, think of it like this. In this reference frame, I have the chalk, and the event is I throw this chalk towards you. Okay? In this reference frame, fixed in the classroom, let's say, you looked at me with surprise, that is an event, and the event that I throw this chalk is a second event. In the classroom, they happened at the same time. So one event, you are over here, me throwing the chalk is over here. Okay, so my throwing the chalk is not in your past at the moment that I throw it. But eventually the chalk will reach you. Basically because you are also moving you are at rest in this reference frame, so you are moving along the time axis. Me throwing the chalk, it has this light cone. The chalk will have this trajectory, not following the light cone. And you have this trajectory. Sooner or later, these two lines coincide. They overlap. At that moment, the chalk hits you. And at that moment, in the future, me throwing the chalk is now in your past cone. Not at the moment that I throw the chalk, but at the moment that it hits you, it was in your past. It will be in your past cone. Because as I said, these light cones, they are moving with you. They are not at rest.
Hocam peki şu ısıya duyarlı füzeler falan hani biz kaçıncı onlarla bizi takip ediyor ya. Bunun light konundan mı nasıl çıkıyor?
You cannot, I mean, you have to run, I mean, you cannot, you see, which light cone are you talking about? Because light cones are always changing. If you want to get out of the light cone of anything, you cannot. I mean, you have to move faster than the speed of light. But that doesn't mean it will hit you. Because you see, for an object to hit you, your trajectories should overlap. They should intersect. Just move in a way that your trajectory doesn't intersect with its trajectory. You don't need to get out of the light cone. What we are saying is something that happens in the past, in your past, might influence you. It doesn't mean that it will influence you. But anything that was not in your past light cone in no way can influence you. Any last questions? So see you on Monday. And well, there are no news that the school will be off on Monday. We will have lectures on Monday. There were rumors that the schools will be closed. The high schools and the elementary schools, etc., they are closed, but not the universities. So on Monday we have a lecture. Unless there is a new announcement.